finally, we have now the theory platform, and Peter van Loock from Mainz will give the overview over this.
Okay, so thank you, Christian, for the introduction. And I have to immediately emphasize that this is by no means an overview talk for the theory platform. So then also apologies to the other members of the theory platform. So I assumed that I was going to talk a little bit more with a focus on my own group, but along the way, I will certainly also put the other groups, theory groups, work in context to what I'm talking about. So yeah, but anyway, I do have a slide also for the other groups, and I will put it in context. I will try to do that. Okay, so and that's why my talk is entitled Analytical Quantum Repeater Modeling. I have to check the time as well, because I'm notoriously late with my talks, not at the beginning, but at the end. So let's see how it goes. So analytical quantum repeater modeling. As I said, the focus is on the theory repeater work in my own group, and we have a certain focus on analytical models and secret key rate analysis, secret key rate analysis using quantum repeaters. As Christoph Becher already emphasized, I think I can basically skip various slides as well based on Christoph's talk. The focus in QRX is on fiber-based long-distance quantum communication. Of course, there are also satellites. This is not our focus in QRX in general, and also the theory work in my group. So it's similar to the classical fiber-based networks that spread the globe. We are going to consider fiber-based quantum communication, and the repeaters we focus on are memory-based. There are also other approaches. I think it was mentioned in one of the previous talks. All optical quantum repeaters based on photonic quantum error correction codes, photonic cluster states. Sometimes they're referred to as third-generation quantum repeaters. So here in this talk, the focus is not really on that, although I have to say we do have a kind of an explorative work package in QRX that is also related with such third-generation quantum repeaters. So to say here, the focus is on first-generation quantum repeaters, if you want to use this terminology. So, and then in terms of the systems and the encoding, we focus on qubits. So it's not really continuous variables, for example, or higher dimensions qubits. It's really like single photon qubits, in particular, maybe based on polarization, and single spins, as opposed to, for instance, collective spins. As also mentioned, I think, by Christoph in his talk, there was a recent experiment with spin waves related to this very famous, prominent DLZ quantum repeater that is based on atomic ensembles, collective spin modes. And it works certainly slightly different from the repeater protocols we are focusing on here related to the three platforms of QRX, because in those, the stationary qubits are encoded into the single spins and not collective spin degrees of freedom. Okay, and then in general, the goal is from the theoretical point of view to design and model the experimental demonstrators, so physically model them and then statistically assess them, calculate the rates, or eventually for QKD applications, the secret key rates. The demonstrators, obviously, the experimental demonstrators are of a small scale. So this is the kind of near-term perspective, but we have also a long-term perspective, and the long-term perspective is towards larger scales. So we want to scale up the repeater, possibly even going beyond a two-party application. Maybe we want to talk about more users, more complex quantum networks. I think this was also touched in the previous talks. And also correspondingly then in terms of these rate analyses, Christoph did focus on the two-segment case. So that would correspond to this small scale near-term perspective. In this talk now, from the theoretical point of view, I want to go beyond. So I definitely want to go beyond the case of just two segments. And of course, this is all within the overall theory framework of previously QLink X and now QRX. Okay, and in our theoretical model, the overall setting, the basic assumption are the following. So we assume quite generally that we have some heralding mechanism to distribute entangled qubit pairs. Of course, we have to send photons somewhat and then connect them to the local spins, so to the stationary memory qubits. So we need to herald the success of this entanglement distribution in one of these segments. For instance, by detecting loss of photonic polarization qubits. This would be one example, but it's not restricted to this particular realization. Of course, I said we do have a focus on qubits, but it's quite general. So all what we assume is that there's some mechanism that enables us to distribute 2 qubit entangled pairs in one of these segments with a certain probability. Of course, this probability then depends on the length of these segments due to the transmission loss in the optical fiber. Okay, and then besides the entanglement distribution, we need some means to connect these segments. So that's the entanglement swapping. And there we also have a basic assumption. The basic assumption is not only that the entanglement swapping probability is constant, it may actually also be time dependent. For instance, in these DLZ quantum repeaters with these collective spin modes, where we have memory loss, it depends on the time for which a qubit or quantum information is stored, how strongly this loss causes errors or inefficiency in the whole repeater. So this is not what we're looking at here. In our case, the entanglement swapping probability is a constant, and even more so, it has unit. We assume unit success probability. So entanglement swapping probability is set to 1. And then, of course, we need the memories. So these are the platforms. The quantum dots are not here. I didn't have a nice figure for quantum dot. John had one, actually, I noticed, and not only one. These are at least 2 of the 3 platforms: diamonds and ions, atoms. This is actually a photo a fairly long time ago I got from Ferdinand Schmidt-Kahler from his ion experiments in Mainz. Obviously, it ends up on my slides always again and again. So these are the basic ingredients. And then our goal from a theoretical point of view is to provide a rate analysis which is exact, potentially optimal. So the goal is possibly to optimize these rates and, well, to be able to consider medium scale quantum repeaters. So maybe I should take up should I do that? Why nobody said this? I don't know. It was okay. Well, now I notice that it's actually also not so convenient to talk with a mask. So the repeater systems are supposed to be of a medium scale. Currently, we can calculate rates for repeaters up to 10 segments in this framework. And so what we are doing here is basically memory-assisted QKD. We are not introducing some means of active quantum error correction. So of course, there's some intrinsic quantum error detection in a way because we have the loss heralding mechanism, but we do not consider any additional quantum error correction codes or entanglement purification in particular. If we want to include this, it gets more complicated, more complex, even for a small scale system. And for this, it is certainly useful to consider numerical simulations. And in fact, there are various groups, well, in the international community who work on such approaches, on numerical approaches. Here's one paper of the Delft group. I think there was also a talk about this particular simulation platform given at last year's workshop here. There are certainly other groups. This is just an example. And actually also in QRX, we do make use of simulations to support the analytical calculations. And there are also groups who push this simulation-based approach a bit more. For instance, the group of Jens Eisert in Berlin, they are looking at event-based schemes for simulating quantum repeaters, which is actually a bit similar to this NetSquid simulator. And so, as I said, if we want to consider a larger system, a large-scale system, which then necessarily also needs to include means to correct errors, to detect errors. We really go to many segments, scale it up to really large distances. then eventually, and this will be also maybe one of the results of my presentation here, where we look at schemes where we don't include quantum error correction, that, well, eventually we will need this if we want to go further. And then it gets more complex. And then, of course, the numerical approach helps a lot. But certainly these things go hand in hand. And I do believe that the analytical approach gives us additional insights into the impact of the different experimental parameters, their trade-offs, the scaling. And maybe this is going to become a bit clearer during the rest of this talk. Okay, so then in the context of the QRX experiments, our goal is to identify these elementary quantum repeater units. They were already mentioned and even shown in Christoph's talks, these quantum repeater cells, half segments. So they serve as some kind of quantum repeater module, and these modules can be put together to go to larger repeater systems and to scale up this repeater. More from a theoretical point of view, in terms of protocols, there are various ways how to do the entanglement distribution and how to do the swapping. These are named here as distribution swapping strategies. I will come to this later. NSP, NRP was also mentioned. These are these acronyms for these particular protocols: node sends photon, node receives photon, which has a distinction in terms of, well, for two segments in terms of the classical communication and whether it is needed or not. So in terms of these elementary clock times of the repeater. Then we may even go beyond the scenario where we interfere two photonic qubits, where each qubit is a single photon in two modes, like two polarization modes. We can also consider one photon interference. In fact, the DLZ scheme is a bit like this. And there's also this twin field QKD, which is not memory based, but one can actually consider a memory assisted twin field QKD scenario as well, and that would be based on this one photon interference. So from a theoretical point of view, we of course we can consider many more protocols, all based on this general basic setting that I introduced at the beginning. And then ultimately, of course, the theory should allow us to, well, give advice to the experimentalists towards building a practical quantum repeater systems with, well, both long-distance scalability and long-distance privacy. This is something I want to stress here again, that the quantum repeater is the only device that achieves both notions simultaneously. Christoph showed these relays with these trusted nodes. Well, they are scalable, but they are not long-distance private. So for this long-distance privacy, we do need to share long-range entanglement. Then these nodes can be untrusted. And that's exactly what a quantum repeater does. But the scalability is tricky, and for this we need the quantum memories. And then a more longer-term perspective is the last point here on this slide: the integration embedding of quantum communication into existing public network infrastructures. This is certainly something where the expertise from the Munich node with Christian Deppe and Holger Boche comes into play. So you see some of the items here are, of course, taken from the broader context of QRX and not necessarily from my group. Okay, and now I come back to this simple model with these three experimental parameters. Maybe I can go reasonably fast through that. We had identified these three parameters: memory coherence time, clock time, link efficiency, a very simple model. And with this, we can already, well, see what happens in the quantum repeater in terms of the scaling. Y-axis is the rate. So indeed the secret key rate for a BB84 QKD scheme. This is the distance. So the gray regime here between these dashed lines, the dashed lines basically correspond to these eta and square root eta transmissions that were mentioned before. So with a two-segment repeater or with a quantum repeater cell, we would ideally be able to reach this upper dashed line. Realistically, of course, if we are lucky, we are somewhere here in between. And the offset here is determined by this link coupling efficiency. We can move up and down. And of course, it's good to start high up here. Then we can enter the gray regime more early. And then the drop, the decline here of this curves, that depends on the memory dephasing and the quality of the memories. And these are just exemplary curves These are not the quantitative curves that are really given for these platforms. We will come to this from a more general perspective later, but well, most of them you've seen already in Christoph's talk. So, but I said, if we are lucky, we are in this regime. I mean, you can think of this simple model as a kind of necessary model that tells us what we necessarily have to achieve in terms of these three experimental parameters. Because here, effectively, the state and the gate fidelity, so all these state qualities and so all these other parameters are perfect. They are assumed perfect. That means if even under these assumptions, we will not be able to enter this gray regime, then we wouldn't be able to do so, of course, if we include these other experimental parameters as well. Okay, and well, I mentioned the repeaterless bound already. That's basically the eta line. That's the bottom dashed line. That's this so-called Plop bound, which was mentioned several times now in the talks. The rate is upper bounded by this eta, where the eta is the exponentially decaying, with distance exponentially decaying function here. And that's a rate that counts the number of secret bits per channel use and per mode. This is not yet per second. This is not in hertz. This is per channel use. This is also something we always have to bear in mind, because the point-to-point link, the direct transmission for which we have this bound, typically can emit optical signals at a high repetition rate, gigahertz, so to say, mostly. That's something we can assume for a point-to-point link. For the repeater, even without classical communication, if we just consider the light matter coupling at all these repeater stations, typically we have something like megahertz. So it's a factor of 1,000 worse in terms of the repetition rate, even without considering the classical communication times. So you see there is a penalty to start with. And there's something, a price we have to pay, and this will pay off only provided we go to sufficiently large distances. We can improve the scaling sufficiently much. And also there's another penalty we have to pay, and that comes from these fidelities and these qualities which have not been considered yet in this simple model. And I will come to this next. So this was still the simple model with these two types of protocols and modules to construct quantum repeaters. And in all these figures, which you can hardly see here, we never actually have a complete drop. We never have a complete drop to zero of these curves. They smoothly go down and decline. This is due to the fact that we have not yet included these finite state and gate fidelities. This is just the memory dephasing. Yeah. And so we will see now soon that if we do include finite fidelities, we can have a drop that really goes down to zero for the secret key rate. So here I have one slide as promised in the broader QRX context. So now I said the goal is to extend the previous theoretical analysis to larger systems, to larger repeater systems, to more complex repeater systems, and more complex systems may also include networks. So here we have multiparty scenarios based on graph states, quantum network routing, graph state methods, and also in the QKD context, device-independent QKD. We had a talk on device-independent QKD, but here even in the multiparty setting. So there are various notions that we consider in a proper network, not only having Alice and Bob. And then, of course, I had one item on a previous slide in terms of this embedding and integration of these quantum information layers onto these quantum physical layers into real service, possibly hybrid with a classical network that is already existing, and looking at all these issues from a more information theoretical point of view is of course done in the groups of Holger Boche and Christian Deppe. So with these, I actually have already mentioned the three groups which are part of the theory platform. So that the group of Dagmar Bruce in Düsseldorf, the group of Jens Eisert in Berlin, Munich with Holger and Christian. But there are two more theory groups, which is the group of Martin Plenio in Ulm and Frank Jahnke in Bremen. And these two groups devote their theory work to more, say, even more platform specific theories and models, namely for Martin Plenio, the diamonds, and for Frank Jahnke, it's the quantum dots. So you can see there's some other theory work done in the theory platform, which is even more specifically zooming into the particular aspects of the different hardware platforms. Okay, now back to the simple model with these three parameters. If we want to go to more segments, we have to include the classical communication time for sure. That's L0 over C. L0 is the length of one segment. So if we go to more than two segments, and now, as I said, we want to include fidelities as well. The state fidelity, so we distribute these initial 2-qubit states in one segment with a certain quality, which has not been included yet in the simple model. And then eventually we will have to do some Bell measurements on two spins, on 2 qubits at one station with some gates, or more directly, I think that was also mentioned in some of the previous talks, how one can do this. This certainly will also in reality be imperfect. So we have to introduce some Bell measurement, or more generally gate fidelity. And then for the protocols, I mentioned that already, we have different ways, different strategies of connecting these segments. So for instance, look at the n=4 case. We can go from left to right. I have a few other slides later, which make it maybe even more clear. We can go from left to right and connect one segment after the other, or we can just double the distances. Maybe that's the most common thing to do here for 4 segments. We connect 1 and 2 and 3 and 4, and then finally the 2 extended segments are also connected. But there are different strategies we can use for the entanglement swapping. And so we identified in the context of our theoretical analysis 3 criteria for an optimal scheme. So the scheme should be fast. That means the initial distribution in all these segments should occur in parallel. I just mentioned this sequential scheme from left to right. This is not necessarily distribution in parallel. This may actually also have an advantage, because in this case, we would at any time step only have at most one spin pair dephasing, because we have not yet started distributing the others. We just do it step by step. So that's a scheme which is rather slow. So in terms of, in the QKD context, a raw rate, it would have a bad raw rate. But it may have a good secret key fraction. So it may offer good state qualities for the final states, good fidelities for the final states, to use this sequential distribution and swapping scheme. And this is the third criterion here: parallel quantum storage as little as possible. So this sequential scheme kind of avoids parallel quantum storage completely. But of course, it's slow, and the accumulated dephasing times in such a scheme are again worse because it's so slow. So you can see we have all kinds of trade-offs here. But the second criterion is certainly a valid one. That's a good thing to do, to always swap as soon as possible, because if we have 2 ready pairs next to each other and they're dephasing, then it's a good thing to just connect them. Then we have, instead of 2 pairs dephasing, just 1 extended pair dephasing. Yeah, so entanglement swapping as soon as possible is a good thing. It is one of these 3 criteria to optimize the rates. And for instance, this doubling scheme would not necessarily always swap as soon as possible. For these 4 segments, imagine segment 2 and 3 have been successfully distributed. We would not connect 2 and 3. We would still wait. So they would just be subject to memory dephasing unnecessarily. So let's again look at the simplest case of 2 segments and just 1 repeater station. So in our theoretical model, we consider 2 basic random variables. These are these K and D variables. The K represents the total waiting time. So basically the average of this, and the inverse gives the raw rate. But overall, it's the total time it takes from the start, when we start initially distributing pairs in these segments, until the final state which is eventually shared between Alice and Bob. So that's the K. And the D is the dephasing. That's the D variable here. And now for this so-called sequential scheme, That was the one I had on a previous slide for n equals 4, where we start left and then we step by step sequentially distribute and then connect. Well, for 2 segments, it would mean, for instance, we start left and distribute. And once we succeed, we do it on the right. That means the total time is n1 plus n2. So these n are just these random variables that are associated with each segment, basically geometrically distributed random variable describing the success process, the distribution process in one segment. But now sequentially, we have to add them all up. I said already, this is rather slow. In a parallel distribution, we would do this in parallel, left and right, and we succeed either left or right. And then the total waiting time is given by the maximum of the 2. So the segment that took longest determines this k, which is the total waiting time. And so that's faster than the sequential distribution. And for the dephasing, we also have a difference here. For the dephasing, we start left and right. And then, well, either of the 2 succeeds, will be stored, and then waits for the other one. That's why we have to look at the difference of these 2. So for 2 segments, this is rather simple. But we want to go to more segments as well. And the good news is that we can stick to these 2 basic variables. And we just extend them. Well, for the sequential scheme, it's rather simple. We just add more of these n's up to n segments. It's just the sum of these. For the dephasing, it's the same. We just don't use the n1 because, well, the n1 is distributed. There's no storage during these attempts. Then once we succeed, we store it. And then this one waits for the second. Then we connect, we wait for the third. So we just sum all them up except for the n1. So that's easy, that's easily calculatable. For the parallel distribution, it's more tricky. Well, we have the max of all these n's. And for this, we have an analytical expression. This has existed already for some time. More tricky is the dephasing now. So we want to include the dephasing, the d. First of all, to write down the expression for more than 2 segments. Well, there are various possibilities that is connected with these different swapping distribution and swapping strategies that gives us different d's, different dephasing random robots. And then the next tricky part is to actually optimize the d. What's the optimal strategy to have the minimal dephasing time? And then you will see that the d doesn't go directly into the states. We have to exponentiate it, e to the minus alpha d, and there's another parameter alpha in front of the d. Which eventually then gives us a part of the secret key rate, the relevant part of the secret key rate. Okay, so the methodology in our theoretical model is as follows. We have these 2 random variables, k and d, and functions of them. And how do we get the statistics of these? Well, our formalism is based on a PGF that stands for probability generating functions. So all we have to do is to get the probability generating functions for certain protocols, strategies, as I mentioned it before. And how do we get the PGF? Well, there's a distinction for K and D. For K, and assuming deterministic entanglement swapping, we can do it via simple combinatorics. We have a closed expression for the rates, but we can also get these PGFs for K. For the non-deterministic swapping case, this is actually already a bit tricky, but one can use a Markov chains or linear equation systems. But mainly we are talking here about deterministic entanglement swapping. Now about the dephasing. The dephasing PGF is actually not obtainable, for instance, via Markov chains. That's why I mentioned it here, this non-deterministic swapping case, because for K it works. For the dephasing, it doesn't actually work. So for the dephasing, we have to do something else. So again, we have to actually do some kind of combinatorics and consider all kinds of permutations of these basic variables. And that means, well, that clearly means we cannot go arbitrarily far. So this puts the constraints on our system. So far we can go up to 8 segments. Maybe we can push it further, but there's certainly a limitation based on the present framework in order to get the PGF for K and for D. Okay, and the optimal scheme then is the one that minimizes the dephasing. And in our optimization, we look at the minimal dephasing among all schemes with a minimal K, with a minimal waiting time. That means that was this K parallel here. N is the number of segments, small n.
So as I said, it's the maximum of all these random variables for each segment. These schemes are the fastest schemes, so they have the smallest total waiting times. And among these, our goal is to minimize the dephasing. So there is the loophole that there may be schemes which are slower, which do not have this k parallel, max n1 through nn, but may still have smaller dephasing. I touched this issue when I talked about this sequential scheme, which avoids parallel storage to a great extent. So we cannot take it for granted. That means we have to actually then really look at specific schemes. And for the towards this optimization, I'm only talking about the optimization. If we are not interested in the optimization, we can calculate these rates anyway. But if we're interested in the optimization, then we have to actually also take into account that there may be slower schemes, overall slower, which may have less dephasing, even though intuitively we may not expect so because they are overall slow, and that's why they have a larger accumulated dephasing. And in fact, for the case of 3 segments, we've confirmed this. So for the case of 3 segments, our optimal scheme, the one that minimizes the dephasing among all schemes that maximize the raw rate, it is just optimal. So that's the optimal scheme. It gives the highest secret key rate among all schemes. And well, later I have a slide with a table where you can see numbers that you can see that this goes to higher segment numbers too, if we look at the secret key rates. Okay, here again, these different swapping strategies. Well, that's basically the doubling the distance. That's this kind of sequential scheme, start left, extend, then distribute here. You may also distribute immediately here, but that wouldn't be wise because then you have to wait because the strategy is such that you can connect here only provided these 2 have been connected. And then you can connect here also only provided we have this distance here. So here it would be really wiser to actually also wait with the distributions, and then we have this fully sequential distribution and swapping scheme. Okay, and now here in this extended model, for the particular case of 4 segments, you can look at these curves that we've seen before. The blue line is this repeaterless bound, it's Plop. The numbers are not so relevant here. I mean, this is an extremely high coherence time. This is just for illustration. This is 400 seconds. This is rather small here. That's basically p-link. That's the coupling efficiency. I just want to illustrate what happens. So we have these lines. We have the drop to 0. That's now due to a finite state and gate fidelity. I didn't even write the numbers here. It's just for illustration. And the dashed lines are actually the raw rates. So the errors are the solid line. The errors are included in the solid lines, including the finite fidelities, but also due to the memory dephasing, we have this general decline here. And now you see the numbers are such that we have a very high coherence time and a bad link coupling. We can improve the link coupling. So now it's 80%. It's pretty good. So you can see it moves up and down. That's what I said before. This is this offset along the y-axis. And then the memory dephasing is related to the slope. And the state and gate fidelities are actually also related with this offset and with these drops to 0. And now if we do write explicitly the fidelity values here, then you can see here numbers like 0.95, 0.97. Well, we have this drop here. I changed them. Here I have a better value for f0, 0.99. And for the mu, it's still not so high, 0.94. We barely exceed the blue line, but it still drops to 0. So I haven't really introduced the f0 and the mu yet. I will do this in a moment. We have basically 2 fidelity parameters for the initial states. That's the f0 and the mu0. You can basically ignore the f0 for the rest of the talk. That's a parameter we introduced because we may also look at different protocols. I mentioned these one photon interference protocols, and when we want to compare with such protocols, these protocols have an intrinsic loss-dependent dephasing, so it's good to explicitly include some dephasing for comparison also in the other protocols. But mainly we will actually use mu and mu0, and not so much f0. So f0 is the initial state fidelity in terms of dephasing. You can see it's 1 here, but important for us are the 2 parameters from the simple model, the coherence time, and the link efficiency, which includes all the other experimental efficiencies, preparation efficiencies, and fiber collection, coupling efficiencies, collection efficiencies. But these are not numbers from the different platforms of QRX. These are kind of representative values, current value, which is not so good, and an improved value, which is pretty good. So 10 second and 0.1 second for the coherence time. 0.7 is the good value for the link efficiency, and 0.05 is the kind of bad value. And then the μ's are the fidelities, or strictly speaking, the channel parameters. It's a depolarizing channel for the initial state and for the gates to do the Bell measurements. And for these, we either assume something like 0.97, or, well, for the ideal case, to match the simple model with perfect fidelities, we set them to 1. Okay, and here we have the quantum bit error rates depending on these μ's. So you can see that here the μ's is important now. If μ is 1, so we have perfect state and gate fidelities. The μ0 is related with the initial states to the power n for n segments. The μ is related to the gates to the power n-1 for n-1 Bell measurements. And so if this factor is 1, it's 1 minus 1 is 0. We have a 0 error rate for the Z variable. This is what we saw for this simple model. That we have only a non-zero error rate coming from X here. And that's due to the phasing, which is in this exponential. So that's our D. That's the random dephasing variable. And so the larger D, the smaller this becomes, and the smaller this becomes, the closer we stay at 1 or at 1/2 for the error rate of X here. That means here we have an impact of the dephasing, but it's an interplay between this and the other parameters, and it's crucial to see whether, well, we have a non-zero error rate in both, which only happens if the μ is less than 1. So we have finite state and gate fidelities, because then we can see this drop to 0. And this is also related with these minimal fidelities. And Christoph asked in his talk whether this number that occurred in one of these contour plots is a universal number. And it is indeed related with this. I come to this in a moment. So that's just the dephasing. And the dephasing is also connected with this alpha parameter in front of the random variable D, this little alpha. This can be referred to as an inverse effective coherence time. So it's the coherence time here, and in the enumerator it's the elementary time unit of our repeater, which, if we have to include classical communication, depends on the segment length. But that's of course also protocol dependent. But in general, it would be something. It would be something like this. And so you see, a alpha small would be good. That means high coherence time, small elementary time units. So if we do have to use classical communication, small segment length would be actually good for alpha, because then we, if this exponential here in the exponent has a small alpha, a small d, little dephasing, but also small alpha, so high coherence time, and if not is 1 and the μ is 1, then we would actually have a 0 error rate. So that means this way we can kind of clearly say what the good parameters are and how they should be. And this is the secret key rate now, eventually asymptotic secret key rate for a BB84 scheme. And basically we take the average of these bit rates on the previous slide. We basically only have to take an average for EX, because there we have a time-dependent variable. That's the dn here. That's our random variable that depends on how long the memories have to store quantum information. And okay, and here we have the 2-segment case. I think Christoph showed maybe this slide, maybe with slightly different values. This is now for the rather bad choice of the parameters: coherence time 0.1 second, p-link 0.05. M is the so-called memory cutoff, which we can use here to optimize the rates. And now you can see we have a fidelity here, which is related to this mu parameter by 3 mu plus 1. And now, well, I go quickly through these slides with different parameters. Here it's, well, bad, good, good, bad, And then here is this the plot where we have a fairly high coherence time and a good link coupling. And you can see there's a big area here where we're much better than the Plop, the secret key rate divided by Plop, around 500. But this is also something Christoph mentioned. You have to bear in mind for such distances here, 700, 800 kilometer, Plop is like 10 to the minus 16. That means an improvement by an order of magnitude of 100 brings this down to 10 to the minus 14, 10 to the minus 13. So in absolute terms, this is still a bad rate, but that's clear because this is a very big distance, 700, 800 kilometer. Here for 2 segments, we would put a station after 400 kilometer. This doesn't have a good scaling. And so we don't really get good rates here, but we do beat Plop. And the minimal fidelities are not so high compared to obviously then going to higher segment numbers, 0.94. So where does the 0.94 come from? I see Christian is already getting impatient. I think time-wise, okay. It's okay. Okay. At least this point, I think I should make clear this this 0.94 here. So this is related to this table here. First of all, because Christoph asked, is it a universal number? It's not a universal number, but it's a universal effect. We will always have some minimal fidelity, but it's not a universal number because what we took here is the BB84 scheme. And what we also assumed is that for these mu parameters, for illustration purposes, the initial state mu and the gate mu is the same. This is not necessarily in an experiment like this. One may be better than the other. And we can calculate this as well. Just for the illustration, it's simpler to have the same here. And because then in these quantum bit error rates, we have for 2 segments, we have mu squared times mu naught. So we have, if they are the same, we have mu cube. So we have a 1 minus mu cube here. And that's exactly where now the value goes in from the table, because 0.92 to the cube, 1 minus 0.92 to the cube divided by 2 gives something like 11%. And now the 11%, if we have an 11% here for EZ, and here as well, and now I may even assume that we don't have any memory dephasing. That means now I'm talking about the sole faultiness of these individual elements. We're not making use of them in terms of storage for a repeater for a better scaling. It's just using these elements which are not perfect, which are these prepared states and the gates. Then, well, this is 1. So you can think of an alpha going to infinite because it's the inverse coherence time, or you can say just D is 0, which actually will never be the case because even if we succeed immediately in the distribution, typically we have a constant dephasing here. But let's assume that this is just 1. The F naught is 1, then we also have a mu cube here. So they're the same, 1 minus mu cube. So which means we would have the 11% here and the 11% here. And that goes into here. And we don't even have to average without the dephasing. So these are just constants given by these mu parameters. And then if you plug in the 11% here for the binary, these are these binary entropy functions, you get something like 1/2 here and 1/2 here, and 1 minus 1/2 minus 1/2 is 0. So then the secret key rate just becomes 0 because the secret key fraction here in the enumerator becomes 0. This would not happen if these mu's are 1. And but quantitatively, maybe that became clear now. It's related with these numbers. So we can, for 2 segments, we cube them. For more segments, we have to take the power n-1 and n for the mu. So for here we get a mu to the 7, for instance, for 4 segments. And then we get a higher requirement for the mu. But then that's the last thing I want to say in this context. We still have to translate the mu into an actual fidelity, and well, the mu is the parameter from the depolarizing channel, and you probably know that then there's a relation between a proper state fidelity and this mu. The fidelity is 3 mu plus 1/4, and now if for 2 segments the mu is 0.92, this limiting mu, and then 3 times 0.92 plus 1 over 4 gives exactly this 0.94. So if you take the other values from here, 0.965 and 0.984 times 3 plus 1 over 4, then you get exactly these fidelity limits, but all given for the special case of a BB84 scheme, assuming that the error tolerance in this quantum bit error is this 11%. There are better values as well. This is based on basically one-way post-processing. There's also two-way processing. So these are QKD specific things. We made an assumption here. We calculate the asymptotic rates for BB84, assuming one-way post-processing, and then we get these numbers. And then we can go to more segments. And now I should approach the end eventually. I think I will skip over the last slides then. So for 4 segments, again, we see a lot of black. And as I said, the minimal fidelity is now higher. Now I told you how to get this number. And so these are the bad coherence time and link coupling values. Now the link coupling is better. Here the coherence time is better. And finally, the good values for both. Again, we have a big area which is bright, which means we have a big improvement over the Plop bound by our secret key rates that we get here. And in fact, now it's already 10 to the 4 improvement. But if we want to do better, then again, we have to go to more segments, but the requirement on the limit fidelity, on the minimal fidelity gets even stronger. And this is what we have here for 8 segments. So you can see this number again went up. And here, these 2 are the bad values, and these 2 are the good values. You can see for the good values for coherence time of 10 seconds and link coupling efficiency of 70%, and a sufficiently high state and gate fidelity. We have a fairly big wide regime, and you can see the distances are already fairly large here, like 800 kilometer, because now we have 8 segments. So we put a station every 100 kilometer. We have a good scaling, and we get a big improvement over Plop. And if you zoom into all these parameters, you can see that the 8 segment case is really a bit special here. So the S here at the bottom in these bottom rows are the secret key rates for 2 different coherence times. And if we set the mu to 1, the state and gate qualities are perfect. You can see we can go to larger segment numbers, and we will gain. We will become better because the raw rates become better. We have a better scaling, better loss scaling. However, the finite fidelities prevent us from doing so. It's not a good idea to go to larger segment numbers unless we include some form of quantum error correction. So that means we have to stay here. How about the smaller segment numbers? Well, the total distance here is 800 kilometers. This is kind of the distance from the most southern part of Germany to the most northern part. So that's why it's kind of it's an example distance of maybe practical relevance, but it fits also nicely into this framework where we put a station every 100 kilometer, whereas for smaller segment numbers, for instance, 2, we have after 400 kilometer, we put a station. We have not very good loss scaling, but there's a second effect here. That is in terms of the dephasing, because this is the average dephasing here multiplied with this inverse coherence time, which also depends on the L0, which is in this case 400 kilometer. So we have a fairly big, compared to these numbers here on the right, a fairly big inverse effective coherence time and not so good raw rates. And this together, but now I was talking about the dephasing, gives a bad accumulated dephasing here, which prevents us from using like 2 or 4 segments. So it's not only the loss scaling, it's also the dephasing for these very long segment lengths. And that's why the ideal choice here would indeed be the 8 segments, which gives us, well, this rate number of secret bits per channel use. And now per second, we have to divide this by the actual repetition time, where again, the classical communication times have to be taken into account. And this is done here, always in the last row. For reference, I have the Plop for L0. That means only for n equals 1, it's the point-to-point repeaterless bound. For the other n's, it's basically the repeater assisted capacity. So that's the ideal what we can achieve using a repeater. And why is this number so high? Well, here for n equals 2, I actually also assumed gigahertz repetition rate, because there's the twin field QKD scheme. This is certainly an overestimation. We will not be able, in a realistic twin field QKD scheme, we will not be able to achieve this. But just as a reference, if we put for total distance of 800 kilometer, if we put a station after 400 kilometer, and we have both high repetition rate from our sources like gigahertz and the scaling that is the same as for a 2-segment repeater, we would get something like this. But here is the number that we get with our 8-segment repeater, well, of the order of 1 to 2 hertz for 800 kilometers, placing a station every 100 kilometer. And more specifically in terms of the hardware parameters in QRX, I think Christoph covered this quite well, and that's why I try to look at this from a more general perspective. And maybe I should stop here. I want to mention one more thing, but I as promised, I skip over these slides. I started with the assumption of unit success probability for the entanglement swapping. If we consider arbitrary entanglement swapping probabilities, which can also be relevant for a realization of a quantum repeater, all this theoretical analysis get much more complicated, and this optimization in particular. So what one can do this, and if you're interested in this scenario, you may look at this paper here, Optimal Entanglement Swapping in Quantum Repeaters, where for this more general scenario with a more general swapping probability, but without considering this dephasing of the memories and optimization of the dephasing. So this is kind of complementary, because here the focus is on the non-deterministic swapping gates. One can strictly, rigorously optimize the rates. And for instance, 4 segments, we get 3 different regimes where each regime corresponds to one particular scheme with one particular swapping strategy. And you may look at this part here of this, probably really last slide, where we have different strategies. For instance, in a 4-segment repeater, if we have 4, 1, 1, 0, 1, 1, 0, so the second and the third segment have successfully distributed pairs, then here we would actually swap them. In this doubling scheme, we would actually not swap them. And also 0, 1, 2, that means, well, segments 3 and 4 have already been extended. This is indicated by this 2. The second segment has a pair successfully distributed, but the first segment is still not occupied with a pair, a successfully distributed pair. In this case, we would swap. So here, overall, we would always swap as soon as we can. In these other schemes, we would actually not necessarily do that. That was pi 2, that scheme. But for instance, if the swapping probability is small and the distribution probability as well, somewhere down here, we get a different, pi stands for policy, pi naught. It's a different scheme where we would actually, in these cases that I just explained to you, we would actually not immediately swap. We would continue distributing first. And this is simply due to the fact that we don't have dephasing here, but we also have a finite success probability for the swapping. So we have to look at this square here, and depending on the values for the swapping probability and the distribution probability, we can identify everywhere the optimal scheme here for 4 segments. And we can also push this a bit further up to, say, 8, 9, 10 segments. So that was it. I should not forget to acknowledge the people who contributed to this work. So Evgeny Shukin, that was basically also a big contribution from him for the last slides that I showed to you. Frank Schmidt and Lars Kamin in particular, who did the work for these contour plots in particular, which gave us a nice illustration. And Simon Reis also works on related issues with repeaters. So to summarize, maybe that's the takeaway message. We have to take care of these state fidelities and gate fidelities. If we don't reach these minimal values, it will not work. And once we reach these values, we go above. We can also, in addition, take care of these other parameters. Of course, we have to take care of all of these parameters. We have basically 3, I would say now 3 parameters. These μ's, these are the state and gate fidelities, the coherence times for the memory dephasing, and the link coupling efficiency. I think these 3 are the important ones if we want to really go also to larger repeater systems with more segments, because then this experimental repetition time is, after all, maybe not so important, because we rely on classical communication. So we have these 3, And maybe 2 out of these 3 have to be good. Maybe that's the rule of thumb. And but for the fidelity parameter, we have to at least go above these minimal values. So then I finish here and thank you for the attention.
Okay, thank you, Peter. So we are already at lunch normally, but we want to take the photo, and perhaps only because you were here already last year and asked answer to the standard questions already, but perhaps you can give your opinion to our new question. Which possibility do you see for quantum technology to contribute to the success of 6G networks?
Okay, I mean, I've seen this email before, so that's why, of course, I was thinking about it a little bit. It was already mentioned before that there is no, if you Google it, you wouldn't find something connecting 6G with quantum resources or communication. So, I mean, what crosses my mind with this question is that I always liked these elementary schemes from quantum information, quantum teleportation, of course. This is what we make use of here for the quantum repeater, entanglement swapping, but also the kind of complementary converse scheme. This is the super dense coding, where basically the roles of Alice and Bob are just exchanged. So Alice does do basically Alice applies a polygate, which normally Bob does, and Bob does what normally Alice does, the Bell measurement. And by this, the goal is to more efficiently send classical bits. So it's not about security, it's really about sending classical information. And in the super dense coding, in principle, I can send 2 classical bits by just sending 1 qubit. But this only works provided that we share an entangled state. And so I think this is interesting, because that means if we have a means to share efficiently or robustly entangled states in a network, there is some application of this potentially to increase the data rate. I mean, this is not about security, this is more about efficiency. I saw a video from last year where somebody also said security may not be of such great interest for the general public. Maybe it's more about faster and better. And some opinions today sounded similar to this. So in this spirit, maybe there are still elementary fundamental schemes from quantum information which have not been fully explored in the context of real applications, and so in this context, I think it could be interesting. And maybe adding to this, in this case, we have to share entanglement, so we have to really store it in a memory, because if we don't use memories in this case, well, we would almost at the same time send the first qubit to share the entanglement, and then the second one to send the classical information. So we also have to send 2 qubits. So the whole idea and concept of this super dense coding is that we have this offline sharing of entanglement. And in fact, in long-range QKD, we kind of reluctantly use memories only to scale it to large distances. But I think for a QKD application, we do not necessarily want to use memories, because Alice and Bob can immediately measure. We're kind of forced to do so, at least in this class of quantum repeaters. But there are other applications where maybe the memories are part of the application. Maybe there's something to add here.
Yes, okay, thank you.